Yeah, hi, my name's Ben Campbell. I'm a sort of specialized quantum physicist, but nobody's ever heard of me. Well, some people might have heard of me, but that's just incidental. My speciality is the quantum physics of space and time, and that is something that is not properly understood, and I've realized that it's not properly understood just by listening to quantum physicists and classical physicists and astronomers. And yeah, well, this goes back to 1959. I was born in 1950, so it goes back a long way. I'm 75 now. So I've been on this subject on and off. I mean, you couldn't, it's so trivial that you couldn't keep on it all the time. But I've been on it for, what would that be, 66 years now. It's a long time, isn't it? Anyway, I started thinking about space and time when I was only 9 years old because I was interested in radio and long wave radio and making my own radio transmitters and receivers. And I studied pretty simple books about Maxwell's equations and things like that. And those were written by really good people. They were contemporaries of Albert Einstein, but they were writing for young people who wanted to get into radio. And nearly everything that I've discovered came from reading a simple pamphlet, really. I mean, it was A4 size, or that sort of size, and it had about 100 pages in it, and lots of helpful diagrams. And from that, I basically got the whole story. I mean, the guy laid it on the block, but I realized that Maxwell's luminiferous ether, electrical engineers will call it the superconductive waveguide of free space, that's real. If that wasn't real, you wouldn't be able to see Dicky Bird. You wouldn't be able to see a quantum of light. You would not. That medium which produces light in our eyes is real, but we don't know where it is. And the only thing that I basically came across when I was 9 was say, well, what if it's in the future? We never get there. You know, it's every instant the future is always in the future. So you never get to the future. You're only in the present. And so what is time? Well, in this view, time is the recession of things that happened in the present, observations made in the present, into the past. And so in this view of looking at time, time is actually an illusion created by the present moving into the past. And it moves in a very systematic way. I mean, we all know that time is the most systematic observation in the universe. And the relationship between time and space is really terribly simple. If something's a meter away from you, or 100 meters, I mean, it doesn't matter what the range is. If something's that distance away from you, it's actually that amount of time away from you, because it took that amount of time, the quanta took that amount of time to get to you. And so you're looking at the history of what you're looking at. You can't look at it now because you're not there. You'd have to be there and you're not. So there's a delay between something happening over there and you seeing it. And if you think that that delay is caused by waves moving through free space, good luck. I mean, that's just classical wave mechanics. But that's not what actually happened. And I noticed, or I was aware from reading that Niels Bohr had argued with Albert Einstein over entangled quanta, because they were arguing about entangled quanta. And Niels Bohr's attitude was proven to be correct in 1972. Now, Albert Einstein died in 1955, so 1972 was 17 years after the poor guy had passed away. And Niels Bohr also went in 1965. So both those guys were dead when two extraordinary Californian quantum physicists demonstrated instant action at a distance. They showed that if you examined entangled, in a nutshell really, if you examine entangled quanta, which are separated, you know, they're the opposite sides of the lab, if you like, then when you look at one quanta, the other quanta instantly knows that it's been inspected. And how could that be? That's sort of instant action at a distance. And I knew why straight away, because both quanta only exist once you've forced them to be determined. And at the point that you force them to be determined, they're entangled, and so they have to. The result found by Clauser and Friedman in 1972 was not only expected by Niels Bohr, but it was only shown to be true after his death, but also the work of John Bell, which gave the statistical mechanics needed to actually provide the theoretical result. Now this is not an extraordinary result. If you do physics at a good physics school, physics department in a university, you will almost certainly do this actual repeat experiment with more modern equipment in the lab, and that's just an ordinary student. And so this is not a weird, peculiar result. This is a systematic exhibition of the universe, instant action at a distance. And so that completely lines up with what Maxwell was saying, because Maxwell was saying effectively that the quanta, the lumps of light, move into his luminiferous ether, which is basically another universe, which exists, as I'd explained it to myself at sort of 9 years old, exists beyond the event horizon of time now. It exists outside our finite space-time, because our finite space-time ends at the present instant. The future hasn't happened yet. When we get to the future, we're still there. And the illusion for us of time is caused by the recession of things that happened in the past back away from us, back into the historic depths. And so I'm now going to show you a diagram which is a slightly more sophisticated version of things I used to draw for myself in 1960. I call it now, I didn't call it then, I call it now the lateral clock coordinate space transform. When we think about classical physics, we think in terms of time being this magic dimension which just goes on and is very consistent moving forwards. But if you want to understand what's really going on, you need to understand how the quantum physical world synthesizes the illusion of time progression. And it does that by moving things that you can see into the past. And the only way you could be aware of that is, well, look, imagine you were blind and you were a physicist and you developed a sort of a LiDAR. So you could sort of see with LiDAR, but instead of having it having those units of depth quoted for you in meters, which is converted by what they call the speed of light, let's just say, I just want to see how long ago it was. I don't care about this daft concept that sighted people have of meters. I just want to know the historic depth. And so you'd find that something that was 2 meters away from you would be 2 times 3.335 nanoseconds away. And, LiDAR is real now. I mean, we really can measure things in space with LiDAR. And the actual raw data, before it gets converted into meters, is actually the time delay in seconds. Well, if you're sending out the light pulse, then the light pulse has to go and reflect off what you're looking at. So you get a time delay that's 2 times the depth in time. And so by 1980, I thought they've got there, because the CIPM, the Committee International of Poids et Mesures, which is French for weights and measures, that's the global oversight body of all national physical laboratories, changed their definition of a meter from so many wavelengths of a particular laser light, which they've been using up to then, and they changed it to the simpler 1/c seconds. Now that's just a very confusing way of explaining reality, because 1/c seconds, if you just take the reciprocal of c, which is 300 million meters per second, that's 3.335 nanoseconds. And so stating that as 1/c is a kind of peculiar way of looking at it. We should understand that spatial separation is the light time of flight, or the quantum observation delay, and that is 3.335 nanoseconds for 1 meter. And that relationship is completely independent of gravity. You could be in the bottom of the deepest black hole or you could be out in free space and you'd still measure the same relationship between what you think of as a meter or what you think of time and space would still maintain that relationship. And so that's why people find Einstein's general theory hard to get to terms with, because it's the units of space and time which remain in harmony, not through the speed of light, just through the fact that the relationship is 1 divided by minus I, which squared, mc squared, c squared is minus 1. Well, that's so obvious that I thought everyone understood that, and but when I realised that they didn't understand that, I thought it's too difficult. I'm not going to study theoretical physics under people who can't even understand that. So they have a strong nuclear force and a weak nuclear force and gravity, and they're all the same thing. They're all different manifestations of gravity, but on fantastically. In the case of the strong nuclear force, you're actually looking at 250 times space-time compression there at the charge phase of a proton. So that's a little bit difficult, because that's 15.5 million times by volume. That's a little bit different than sort of thinking of something as being a little bit bigger or a little bit smaller. There's a diagram which we can put up, which it sort of explains this. Why is this computer not working? All right, I got it to come on now. I'd like you to look at this diagram. I call it the lateral clock coordinate space transform. Now, the observer, that's always you, but it could be your mate next to you, but if you're talking about hundreds of years. But if you're talking about nanoseconds, then it's you, it's your eyes. But the observer is positioned where the arrow says the location of the observer of the space-time anywhere upon the event horizon of now. I've already explained what I mean by the event horizon of now. That just means now, this instant now. And what you see there is the blue axis, which is a which I'm showing horizontally there. I'm calling that the depth of the observed space in any 3D radial axis. So there are 3 dimensions to space, we all know that. But just take any line in any direction, it doesn't matter which direction, just the direction you're looking. You can only look in one direction at a time. And along that line of sight, you're looking at things that are that amount of real time. It really does take that amount of time for that light information to get to you. And so it's moving towards you. The observation is light quanta that are moving towards you. That's why I show the units there as negative, -1, -2, -3, -4. And the relationship between that distance off, if you like, or that spatial separation to time is that as you look at that, you're looking at something from the past. And so I show that as the imaginary historic depth on the purple or mauve axis. And I'm just showing that as 1I, 2I, 3I, 4I. Now, trust me, in 1959, I didn't know enough mathematics to put I there. I was just calling it imaginary. And it was quite a shock to me to realize that that's exactly the same imaginary that mathematicians talk about. But anyway, so on there, very faintly, I'm showing the observation horizon. In other words, you can only ever see something that's on that green pecked line, because you can only ever see a matching between the historic or the spatial separation and the spatial and the historic depth separation. And so that dotted line, that 45-degree dotted line, is what you call C. That's what you call the speed of light, but it's basically nonsense. It's the apparent wave velocity. If you imagine waves, then yeah, these waves, if they were real, they're not, by the way, but if those waves were real, then that's the velocity that they would have, 300 million meters per second or something like that. But it's actually caused by quanta jumping from the past, your past, into your present instantly. And the instant jump is delayed by us because that quanta has to pass through Maxwell's luminiferous ether, which is another universe. So there's a comment there. The units within this space-time field are non-specific time and I-time imaginary time. I'll just abbreviate imaginary time to I time. And those, if you look at the two arrows in the diagram, there's a blue arrow and a purple arrow, and that's just showing what the scaling is. It's anything you want. 1 nanosecond, which is a billion, 10 to the minus 9 seconds, a very short amount of time. So short that most people, only electrical engineers and quantum physicists and people can understand that. It's such a short instant of time. But that's actually 30 centimeters of space. And if you want to put it into spatial units. But really, you should just leave it as 3.335 nanoseconds per meter, or 1 nanosecond for a third of a meter. So that's a nanosecond, yeah? And if Newton mentioned this, by the way, this is not new thinking. If you read the whole of the Principia, Newton says there's this magic dimension of time, and we need to deal with it. Now, I can either imagine now as being fixed with the time going into the past, or I can imagine the present being there and the future going off to the right, or my right anyway. And Newton mentioned that my choice of saying that now is my fixed frame of reference and I'm thinking of time going into the future could be wrong. It's just a convention of classical mechanics. And it's actually, Newton even mentioned that it's probably the wrong thing, but nobody paid any attention to Newton anyway. I mean, he was too clever for most people. And, they just sort of took a few equations and a few diagrams, said, yes, I've got it. Well, actually, you didn't. Yeah? I mean, Newton is the man. I mean, Einstein helped a bit because when Einstein came up with his general theory of relativity field equations, the only person who could have possibly understood what he was talking about, including Einstein himself, he didn't understand it. He just came up with these equations, partial differential equations. And if Newton had still been alive, he said, well done, Albert. I came to the same conclusion myself many years ago. So people think that Newton was wrong about gravity. Absolutely not. He was spot on. I mean, he even mentioned the fact that what he was talking about was basically nonsense, but it's useful nonsense, if you know what I mean. So Einstein and Newton would get on like a house on fire if they'd ever been allowed to meet. But Newton had been in pushing up daisies for 200 years before Albert Einstein came along. So there's very, very few people out there who work on this and who make progress, and I'm one of them. But it's just like Galileo. I'm saying that our understanding of the universe and the cosmos is completely distorted and wrong, and nobody really wants to know it. In those days, people think that Galileo was persecuted for religious reasons. Absolutely not. The Roman Church couldn't give a toss about space and time and planets and things like that, and whether the sun goes around the earth or the earth goes around the sun. It's just that they had a very lucrative monopoly teaching the science of Europe, the wealthy families, young men, because women didn't go to that kind of thing in those days. And they had this lucrative monopoly, and it really was. I mean, people had to pay a lot of money just to have your child go and live basically with monks, like a monk in one of their teaching establishments. And they've been making a lot of money from it. It was a good scam. It was a good game, like selling cocaine to people on the streets is a good game if you can get away with it. Well, they've been getting away with it for years. And people in their position, wealthy, powerful people, such as the priests who run the Inquisition, cannot afford to be made to look ridiculous. So anyone who's they could understand what Galileo was saying. They didn't care a toss about it. But you're not allowed to make us look ridiculous. So they persecuted him and put him into house arrest. But, these days, you can't persecute me and put me under house arrest because, I'm completely innocuous. And all I'm trying to do is help quantum physicists to understand space and time better. And if you want to take this any further, you can find the lateral clock coordinate space transform, the paper. It's 10 pages. It will only take you about 15 minutes to read. And that's actually published by a physics journal. And there'll be a link at the bottom of this video to that. There's a companion paper to that one. Once you've got your head around the lateral clock coordinate space transform, there's a companion paper to that, which you should read as well, maybe once you've understood what I'm saying with the lateral clock coordinate space transform paper. And that's called The Last Tango of the Finite Graviton. Now, I developed the title, the physics title, The Last Tango of the Finite Graviton, in 2016. So it's been, even that's been around for 9 years. And there are people who've heard this strange idea that there's a book or a concept called The Last Tango of the Finite Graviton. And that's now published on a proper peer-reviewed physics journal. And that'll also be linked at the bottom of the video. So thanks for listening to me, and good luck.